All right, so we learned last class about the concept of electric potential, and what we did with that is we looked at a couple of examples of how electric potential works um, in a constant electric field for point charges. And so what we're going to be doing now is we're going to, much in the same way we dealt with electric field stuff, we are going to be developing what electric potential looks like for various other charge configurations. So there's a couple more things we can do with point charges actually. So let's get into that. So dipoles, right? We had a whole thing about dipoles when we did electric field stuff. And so we can characterize the energy of a dipole and therefore then connect that to electric potential. So we'll talk about the energy. So you're familiar with what we talked about before. In the presence of an external electric field, a dipole will experience a torque if there is an angle between the electric field and the dipole moment vector. Remember, the dipole moment vector is a vector that points from the negative to the positive charge in the dipole, has a magnitude equal to Q times S, where Q is the magnitude of the charges. And there is no translational motion in a uniform electric field because the forces are equal and opposite, but they do occur about the center of the dipole, and therefore they will induce a rotation. So in order to figure out the energy associated with that, we'd have to integrate the expression for work. So in this context here, we had developed an expression for the torque, right? It's P cross E. And what's variable in that torque is the angle of the dipole. The P and the E are constants, so they come out of the integral, and so you're just integrating the sine function from initial or final angle. And so when we do that, we end up with a cosine, right? And so this ends up being a difference between these two quantities here. And if we identify the fact that the if we identify the fact that the change in potential energy is equal to minus work, which it always is for conservative forces, then we see that each one of these terms do represent a potential energy of the dipole. And it's given by this quantity down here, Pe minus Pe cosine theta. And so having a cosine here means that if you look at the cosine function, where's my little pen here? So your standard cosine function looks sort of like this, right? Oh, come on. Try this. Yeah. So your standard cosine function from, say, 0 to 180 starts up here, comes down like this, right? And so the positive values of the function are between 0 and 90, and the negative values are here from 0 to from 90 to 180. And so what that means is in its stable configuration, right, that there is, we say that there is, the angle is 0, and so we're up here at the top of the cosine curve here. As we rotate this thing, if we have it upright, then it's at 90 degrees, and we say that the energy is 0 at that point. And then as we rotate this all the way around so that the dipole moment vector points opposite the electric field, then we say we have a bunch of positive potential energy, right? This is the cosine function. There's a negative in front here. So what we see is we have this, this thing here, if you flip this, that's effectively what your dipole energy looks like. It has a negative value when it's in its stable position. Perpendicular, it's 0. And then when it's anti-parallel, it's at its most positive value. So again, individual values don't matter too much, but when you compare things, you could see, and that's why there's a difference between the stable and the unstable configuration. At the unstable configuration, you have the greatest amount of potential energy, so that when you nudge it, this thing will flip around. So the 0 point's actually when it's perpendicular, right? When it's completely stable, it has this lowest value of potential energy, which is some negative quantity. But that's just the nature of the cosine function. That's why we did that. So let's go ahead and rank here the potential energies of the following configurations. So let's do this. I'm just going to draw over this, I guess. That we're comparing is minus PE cosine theta. And the cosine is the angle between electric field and the dipole moment vector. So remember, that always goes negative to positive. So just to be clear about that, I'll draw them in here. Got this nice lavender arrow today. I'm loving the lavender. Very excited about the lavender. So I'm going to draw all those lavender vectors in here. And as you can see here, is anything... we're going to go smallest to largest. So the smallest would be the one that's lined up at the field. That's D. So D goes first. And that has a value of minus PE. That's the lowest the potential energy is. And then anything that's at a slight angle, there's a 45-degree angle or so here in B. That's the next largest. E and F are identical. They're both perpendicular to the field. And that's the configuration of the 0 point. Your cosine is 90 degrees. Well, cosine of 90 degrees is 0. So E and F are the same. Then C, and then A is anti-parallel. So with A being anti-parallel, the value of the potential energy is PE. That's the largest. So the entire range of the potential energy is 2 PE. And but anyway, that's how we rank the configurations here. So here's how the electric potential looks. If you remember, we had not a problem, but a question in the last class where I asked you what the electric field and the potential is from a dipole. And what we found is that in the middle, it's 0. The potential is 0. You can see that in the elevation graph here. As you get closer to the positive charge, the value goes up. Closer to the negative charge, it goes down. Remember, ultimately what matters here when you're doing energy problems is the voltage, the potential difference. An individual value for potential doesn't have a lot of meaning. And so each one of these lines here represent different equipotential surfaces. They may represent, 10 volts. So from the middle line over, it's 10 volts, then 20, 30, and 40, so on. That's how that works. Now, the figure on the bottom here also shows equipotential surfaces, but what it displays here are the associated electric fields. You've seen the electric field picture before, but something are going to want to notice about this is that every place where a line crosses an equipotential surface is at a 90-degree angle. Okay, so right over, every location. So right here, there, right at the moment it crosses the line, it is a 90-degree angle. And that is it's at least a visual connection between the two concepts here. Mathematically, we're not going to get there today. I think that's something we're going to cover next class. But yeah, just take notice of that, I guess. All right. Okay. So, one more example of a distribution, not distribution, but a collection of point charges is the quadrupole. You did a little bit with a quadrupole as far as electric fields are concerned, I believe, on a homework, actually. Yeah, but let's look at how this problem's done. So that would be right here. Okay, so the electric quadrupole has total charge 4Q because quadrupole. Right? But the way it's configured is that we have two positive charges that are equal distant from a negative 2 charge in the middle. And we want to determine what that voltage is going to, what the potential is going to be. So we want it where? On the y-axis, huh? So somewhere like up here. Somewhere up here we can do. So anyway, we have our expressions kq over the distance. So for the positive charges, kq over either y minus s or y plus s is how far away the positive charges are. And the negative charge is just our y coordinate. So that's very simple. That's the top, middle, and bottom charges. But now we need to do a little bit of algebra here to simplify this, because it can be simplified. And so if we do that, we get a big common denominator here. Common denominator is y squared plus s squared, because y minus s and y plus s is a difference of squares. All that stuff gets multiplied at the top. I factored a 2q out just to remove the clutter. A lot of things cancel out, as you see here. Y squares cancel out with the minus 2y squared here. We have ys that cancels out. That's the electric dipole, but we don't have a dipole here. In fact, what happens is when we simplify all this stuff, we're left with a positive 2 s squared. And the 2s squared is another type of electric moment. It's a quadrupole moment. And so we define that as being 2q s squared. We have a capital Q here. Probably not the greatest choice for a letter, but that's what we got. And we end up with kq over what the common denominator was. And if we let y get very, very large with respect to s, then the bottom just becomes a y cubed, which is what we expect for any kind of dipole, quadrupole, anything, any kind of poles you want to talk about. They always go as a y cube. So that's nice. All right, anyway, enough with the point charge stuff. Let's start to do something that's a little bit more interesting. So we want to start to deal with continuous distributions of charge. No more point charges here. We want to do that. And anyway, so if we have a uniformly charged sphere of radius capital R, the electric potential is going to be the same as a point charge. Okay, it's identical to a point charge, right? And but you got to take that distance r to be from the very center of the object. So once you're outside the object, the potential drops off as a 1 over r quantity. And we can prove this later. I'm just going to state it for now, but we'll be able to prove this in the next lecture, because we've already determined that the electric field, due to a continuous distribution of spherical charge, is a point charge, whether it was a conductor or an insulator, actually, right? And so it makes sense that if the electric field behaves as a point charge, the electric potential will behave as a point charge. We can derive that, but I'm going to wait till the next lecture to do that because we're going to learn a little neat mathematical trick that allows you to figure out your electric potential if you know what your electric field is, and vice versa, by the way. Okay. The potential will be the highest at the surface, which we call V naught. So if you happen to know that value, you can create a proportion out of this equation up here. And that proportion gives you the following statement down here, which I don't really like to show you this, to be honest, because I don't like to create equations that are derived from very simple derivations. Yeah, like, this is not a hard formula here. And so having information about, like, say you had the information about the potential on the surface. So you say you're told how large the sphere is. You're told what the potential is. Well, you just solve for Q, and then you use this again at some later distance R. That does allow you to create this proportion, which is a very simple thing to do, but I don't want you to look at this thing down here and be like, oh, this is another equation that we have to do. No, it's not. The potential of a point charge is your equation. And you can create a lot of mathematical tools to simplify things. So this is not a new equation. This is just a proportion. So that's why I don't really like to show you that kind of stuff, because you don't need more equations. You need to understand the concepts and be able to use the equations. Having more equations, the more equations you have that are not completely fundamental and core to the understanding is going to take away from understanding the concept here. Okay, great. This plasma ball is a little wild right now. Never had one that was this crazy. So, I don't know. Let's see. What? Let's keep going then. All right, so let's do a problem here. A proton is held at rest and then released just outside the surface of a metal conducting sphere held at 1,000 volts. We want to calculate the speed of the proton when it is 1 centimeter away from the surface. So now, if you're calculating the speed of the proton, this is an energy problem, right? And if the proton is going to start at the surface and then speed up as it moves away, well, that's an energy transformation that is electric potential energy into kinetic. In energy conservation, it will dictate that the initial potential energy, which we now call QV sub I, plus the initial kinetic energy is going to be equal to those quantities at a later time. Now, a proton starts at rest, so the kinetic energy is 0 to start. But there is a potential to start, and that potential is the value of 1,000. Okay. Over here, when we move a centimeter away, we're at some lower potential over here, right? Which we'll have to figure that out, and then we can work out what the kinetic energy is, and of course from there determine the speed. Well, we got to figure out what this new potential is here. We start off at 1,000, and we're now a centimeter away, and it will drop. But you can't put in a centimeter because we're not a centimeter from the center, right? When you do this problem, it's from the center of the sphere out to where the charge is. And according to this, it looks like it's 1.5. So our initial charge, the initial state, the distance is half centimeter, and then the other charge is at a distance of 1.5 centimeters. So the ratio there, I don't know why I put decimals here. They don't need decimals, but anyway, it goes down by 2/3 basically. Okay. Actually, well, it goes down by 1/3. Well, no, it goes down by 2/3. Anyway, all right, so if we get 333 volts, that's the potential out here. So we know the potential difference. The potential difference is, what, 667. So 667 is the potential difference. But I'm going to put everything in here. The charge is a proton's charge, which is the fundamental charge. And we solve for a velocity here. Make sure you put in the correct mass for the proton, 1.67 times 10 to the minus 27 kilograms. And we end up with a speed of 3.67 10 to the 5th meters per second. Okay. So there's actually several things going on in the problem here. One was, because this is a spherical distribution of charge, there's a formula to figure out what the potential is at some later distance. And then we have an energy problem. And so it's kind of combines two things together. Now, what I was going to mention to you earlier is this, right? So we're a centimeter farther away, and we see that our potential went from 1,000 down to 333. Now, we don't talk about the potential inside of the sphere with this formula, though. So if I'm like, well, what's the potential at, say, 0.25 centimeters, which would be somewhere inside the sphere? Well, there's no formula for that because there doesn't need to be a formula for that, right? Because what is the electric field inside of a metal conducting sphere? Right, what is that? Somebody tell me, chat.
0.
There we go, 0. That means if it's 0, that means there shouldn't be a potential difference inside the sphere. If there's a potential difference, then there is a change in energy that can occur. So once you reach the surface here, you're at 1,000 volts. And as you go inside of it, you are also at 1,000 volts. The entire interior of the sphere is fixed at 1,000 volts. Okay, and it's because the electric field is 0 inside the conductor. We can't have a difference in potential. Whatever the surface has is what it will be inside. Okay, and then the logic behind that is sort of the same thing we talked about when we talk about electric fields. If there was a potential difference, then charges would move, right? Charges would move, a positive charge would move to lower potential, and things would be picking up speed, and that means there has to be an electric field, but there is no electric field. So that's a very important concept here. When you're dealing with conductors, your electric field inside is 0, and therefore the potential inside is a constant. It's not 0. It's not 0. It's a constant. What's the constant? I don't know. It depends on the problem. I mean, we know what the point charge is going to be, right? Let's go back to the slide. For a conducting sphere, acts as a point charge. So what you can do is, if you happen to know how much charge is on your sphere, then you put in that charge here, and for R, you put in capital R, and then you can work out what the potential is, right, at that location. Or if you know the potential at any place outside of the sphere, you can use the distance and the potential to solve for Q, and then you can do what I just said here. Okay? So be careful about that, though. It's very tricky. If I were to hypothetically, on a future exam, ask you what the electric potential is inside of a conductor, and you say 0, I will be disappointed. Let me just put it that way. It will make me a little sad. So don't do that. Okay. Let's do another problem that seems pretty straightforward and it's a straightforward problem, but it's a little complicated. What you want to know what the potential difference is between points A and B. Right? Now, one of them is going to be at a higher potential. Let's see here. Remember, the potential is basically a ratio of Q over R. So this sphere over here on the left has 4 times the charge, but it's 6 times bigger. So B is actually going to be at a higher potential than A. B is going to be a higher potential than A. So anyway, we got to work out both. So for both point A and B, we have to work out 2 electric potentials. Okay? And then we subtract them. Well, we work out 2 electric potentials for A and 2 electric potentials for B. And then we subtract them. So let's do that. All right. So for all of the things that we're going to do here, we have to work out, 1 over 4 pi epsilon naught Q over R, or KQ over R, whatever you want. Let's do the point 8 one first. For point A, we have to work out what the electric potential is due to the charge on the left and the charge on the right. The charge on the left is at 100 nanocoulombs. So, zoom in a bit here. So, you have the radius, or the diameter of these things. So, how far are you from the center of the 100 nanocoulomb charge? You are 30 centimeters away, so a 0.3 goes down here. How far are we from the center of the charge on the right? Well, it's 100 all the way across, so the difference between the 30 and the 100 is 0.7. All right, so, and I'll do this in my beautiful lavender color, but we're working out this distance for the charge on the left. Hey now, what? What's going on here? Oh, okay. Oh, go away. I'm having technical difficulties. Oh my goodness, this is getting out of hand. Let's try this one more time. All right, for A, there is the distance from the center to A. There's 1. And then from the center of this one over to A. So that's your 0.3 and your 0.7. You got to do the same for B. So let me clear this out, and I'll use another beautiful color, which is this lime greenish color. It's not quite lime green. It's like a grass green. It's a healthy grass green, and that's not the correct line there. So for hold on here. Having a tough time here. Let's see. Let's do this one. Okay, so for B, we want this short little distance in here, which is just what? 5 centimeters. That's the second term here. And then we want this long distance that goes from the center all the way over to B. So I have their respective charges and how far away they are from those charges. You can see B is bigger once I plug all these numbers in. And I subtract them for a grand total of, I did minus 2,100 if I decided to just start at B and move towards A, because B is a higher potential, A is a lower potential. So I happen, for no particular reason, because they didn't tell me I have to do this, but I happen to go from B to A. So A is the final and B is the initial. So I end up with a negative 21,000. What I did here is, ultimately the question asks, what is the potential difference between the points? Could be positive, could be negative. You just got to make sure that that you specify, which direction you're going. Ultimately, B is higher than A, right? So if I were to put down a positive charge anywhere between A and B, we could see it would go to the left, because the left is the direction of decrease in potential, and that's would be the direction of the electric field, in this case. All right. Not. Well, okay, so the spherical charge is simple to do because it behaves like a point charge. So that's one easy continuous distribution of charge. Other distributions of charge are not so simple. And what we're going to have to do is we're going to have to break those things up into infinitesimally small point charges. All right. So we want to find the electric potential of a line of charge at a point that lies on a line that bisects the rod. Okay. So you've done this before, except this one's a little easier because there's no step 3. So before we had electric field stuff, we had 1, 2, 3, where 1, which is the same as it is here, is how do you express your DQs? This is linear. There's only one way to do it, and that's your lambda times your differential distance, which will be dy here. Part 2 is to specify what r is. Where are all of my DQs relative to my point of interest? Well, in any particular position along the rod here, we use the Pythagorean theorem to express what that distance is going to be. So that's just our x squared plus y sub I squared, where y varies, not x. All right. And those values of y will vary from minus L over 2 to L over 2. Okay. That's it for the integral. It's just dq and r. There's no r hat. R hat is direction, and there's usually a third step to indicate the direction. But electric potential is a scalar. There's no direction. So there's no step 3, there's no r hat, which makes things much nicer to do. We plug all this in. I am going to double the integral because it's symmetric about the x-axis. So whatever the upper half contributes, the bottom half will contribute the same. So my limits now go from 0 to L over 2. And I'm left with this little tricky integral here. It's 1 over radical constant plus variable squared, which I'm assuming it's a trig sub. Every time I don't know how to do an integration, it's always some stupid trig sub. But you get a natural log out of it, which is quite odd, to be honest. But that's what we get here. So anyway, the lambda comes out, factor 2 cancels, and I'm left with this ln y plus radical y squared plus x squared. And I evaluate through the limits, and I end up with this expression right here. That is what the electric potential is at a point somewhere along the x-axis, right here. Okay, so the y's were variables initially, but now this is a function of x. And if I want to know what the potential is at different locations along the x-axis, well, guess what? I just plug in different values of x here. Okay. All right. That's it. That's it for this one. So let's do one more. One more is this. We're gonna be a little. Want to find the potential of a charged disk. Charged disk. Well, before we did rings, right? But we can just skip over the ring part because we've already seen how that's done. I start with my integral expression, and I have to figure out my dq. Your dq is going to be a to dA, where dA is some infinitesimally small area, which will be a ring. In this case here, it'll be a ring. And so that ring is, if you just take that, roll it out, that is a circle, basically, that's extremely thin. So the circumference of that circle is 2 pi r. That's some random distance r from the center. And the dr is the thickness. So this is a rectangle that represents the area of my infinitesimally small rings. So I got that part. And then we did the same thing we did electric field stuff. I have an r prime here to indicate that that's my distance here, because I got 2 r's going on here. And by using the Pythagorean theorem, we can see that this will be equal to radical r squared plus c squared. Again, no step 3 here. We don't have to worry about directions. In this case here, r varies from 0 to capital R. Okay. So I put everything in here, and I end up with this nice u sub integration. So the rest of it's just mathematics. I get through the mathematics, we end up with this statement right here. So the front of it looks familiar, doesn't it? Eta over 2 pi epsilon naught, but that's just the electric field. The potential has some extra junk on it, which is the junk right here. And interestingly enough, if we plug in a value of 0 for z, so that means we're actually at the center of the disk, we end up with this expression here, eta times r over 2 epsilon naught. And so that will be true right at the center of this thing here. And if this is some kind of conducting disk, if it's a continuous disk, you'll have, you want to work out other places on there. It's going to be a little more tricky. But that's it. So the integrations are rather simple. What's actually nice about these is that what we're going to learn next class is that you can take these expressions for the electric potential, and through a derivative, actually, you can figure out what the electric fields are, which in some cases is easier, to be honest. We work out electric potentials, then we work out electric field. Okay, there's no Gauss's law that we have for electric potential. There's nothing equivalent to that. So this is our technique. Is just the integration. So.